This is the second in the series of log videos. So in this one, we're going to step it up a notch and solve log and exponential equations. Now there's one log property that's used over and over again. I'm not going to give the proof for it here, but I'm just going to show you how it works and emphasize that you really need to know this property. So anytime you have a log expression like this one, the log of a to the b, if you have an exponent, you can take that exponent and move it down front. So that's equal to b log a. Let me give you a numerical example. So for example, if we have the log of 100 squared, that's the same as 2. We take that little exponent, move down front, 2 log 100. And that example should make sense because the log of 100 means 10 to the watt power is 100, which is 2. So this is 2 times 2, which is 4. And the log of 100 squared on the left-hand side, if you squared 100, you'd end up with the log of 10,000. And the log of 10,000 is 4 because 10 to the 4th is 10,000. But just for emphasis sake, be sure you know this property. It's going to be used a lot in logarithms. And it's simply you move the power down in front of the log. All right, let's take a look at an example of where we're going to use that. Well, let's say we had the log problem, the log of 40 base 6 equals x. Well, previously we'd learned that this means 6 to the x equals 40. Well, unfortunately, that one you can't do in your head, so we're going to have to go to the calculator and let it help us on that problem. So how do we do this? Well, the first step is to write it, as I just did, write it exponentially, and now take the log of both sides of that equation. So we take the log of the left-hand side and have the log of 6 to the x equals the log of 40. And now we're going to use that property I just showed you a few minutes ago. When you have an exponent inside of a logarithmic expression, you take that exponent and just move it down front. So this is x log 6 equals log 40. At this point, we want to solve for x, so to isolate the x, we're going to take both sides of this equation and divide by the log of 6. So it's the log of 40 over the log of 6. Now it's time to grab the calculator, because the calculator is programmed where you see the log button on the program. It's programmed in base 10, and that's what both of those mean. This means 10 to watt power is 40. This means 10 to watt power is 6. You really don't have to worry about that. You just punch them in on your calculator. You just type in log 40 and then go divided by log 6, and you get approximately, I'll round off to the thousands here, 2.059. And that should make sense. If you look back, I always like my answers to make sense. Look back at the original problem. Does that make sense in that problem? Well, that means 6 to a power little more than 2 is going to equal 40. And if you think about that, 6 to the power of 2, 6 squared is 36, and 40 is a little bigger than 36, so the power is going to be a little bigger than 2. So I always like to think about my answer when I get it and see if it's sensible. If you got something like 6.043, you knew that wouldn't make any sense. Let's take a look at another one like that. Let's go the log of 7 base 3 equals x. Again, first step, write this as an exponential equation. 3 to the x equals 7. Take the log of both sides. The log of 3 to the x equals the log of 7. Use the power property. Pull the x down front. X log 3 equals log 7. Divide both sides by log 3. Log 7 over log 3. Go to the trusty calculator and type in log 7 divided by log 3, and I'm getting 1.771 to the nearest thousandth, and that's our answer. Does that make sense? Well, 3 to the 1 power is 3, and 3 to the 2 power is 9, and this is between 1 and 2, and 7 is between 3 and 9. So yes, that makes sense. Now when you get good at this, some of these steps within this process, you can skip. The power property where you bring the x down, you can kind of combine these two steps together. Save yourself a little bit of time. When you see the problem, you You really don't have to put in this step once you really know what you're doing. As long as you know what you're doing, you can skip a couple little steps in the process. Let's take a look at where we move the x to a different position. Let's go the log of x base 4 equals 2. Now this one you could actually do in your head, but we're going to kind of do it the long way. This means 4 to the 2 equals x. Well, we know the answer is 16, but let's kind of do this the long way and see what happens. Take the log of both sides. 2 log 4 equals log x. 2 log 4, you could type that into your calculator. Now this is kind of a silly example. I'm doing it on purpose just to show you that oftentimes common sense will save you a lot of time and effort. And there's more to that decimal. Equals log of x. Now I'm going to rewrite this exponentially. So what does this mean? The base is understood 10, so 10 to the 1.20411 power equals x. So if I go to my calculator and go 10 to the previous answer power, I get 16. Now, that's kind of the long way to do a very simple problem. So the moral to the story here is half the time on these log problems, common sense is going to save you much work. Just think of what does the logarithmic expression mean? It means 4 to the 2 equals x, and 4 squared is 16. So in this time, it was really silly to go through all the steps. The main time you have to go through all the steps is when you're given a number. I'll show you. A number here and a number there, and the x there. That's when you really need to use logs. So what does this mean? This means 5 to the x equals 16. I'm going to skip a step, take the log of both sides, and pull the power down all at once. So it's x log 5 equals log 16. Divide both sides by log of 5. And I'm not even going to write it out this time. I'm just going to go straight to my calculator and go log 16 and divide that by log 5 and see what we get. And then again, I'll think about that. Is that a sensible answer? I'm getting to the nearest thousandth, 1.723 to the thousands. 5 to what power is 16? Let's think about that. Well, 5 to the first is 5. 5 to the second is 25. And yeah, 16's in between there somewhere. So the power has to be between 1 and 2, and that's what we got. All right. Now we're going to take a look at solving exponential equations using logs, and this is the main purpose of logarithms, to solve equations where the exponent is a variable. So let me scroll down here, get a fresh page. Since this is a little bit tougher, we need plenty of room to write this out. We'll start off with one that's not real easy. 8.2 to the x power equals 64.5. Well, here's the key to the problem right there. You see x as the power, so you know you're going to have to use logarithms in order to solve this equation. So we take the log of both sides. I'm going to skip the step by pulling the power down immediately. So I got x log 8.2 equals log 64.5. And now it turns into a pretty easy problem because all you have to do to solve for x, take your calculator, take the log of 64.5, and divide by the log of 8.2. Now, as I do that, you should be thinking, what is a sensible answer? Well, 8 to what power is 64? That's 2. 8 squared is 64, so it's going to have to be somewhere around 2, probably a little less than 2, so I can go in on my calculator, log of 64.5 divided by log 8.2, and getting to the nearest thousand, 1.980. Well, that was a good guess. All right, let's bump it up one more notch. How about 2 to the x plus 1 equals 7.31? A little bit different on this exponent. We got another integer added on to the x, so we're going to take the log of both sides. Same process. This time I'll put the step in to avoid confusion. So we just take log, put it on both sides. Log 7.31. And applying the power property, the power can come down front, as we've done several times now. So this is, let me move up here in the second column, x plus 1, which I'm going to put in parentheses to avoid confusion at this point, is that quantity times the log of 2 equals the log of 7.31. We're trying to isolate the variable, so I'm going to divide both sides by log 2. You want to get all your logs on one side. So I've got x plus 1 equals, I'll write it out, log of 7.31 divided by the log of 2. Now I'm trying to solve for x. I'm going to go ahead and write this, take that 1 to the other side, and I'm going to write it out to show you the logic here. So we have the log of 7.31 divided by the log of 2 and subtract 1. Now I wrote it like that because you can do that whole thing on your calculator in one step instead of doing it in 2 steps. So you just go to the calculator, and I shall do that. The log of 7.31 divided by the log of 2 and then subtract 1. Now I'm getting an answer of 1.870 to the nearest thousand. 870. I'm going to take a look at the original problem, see if that makes sense. Well, 1.780 plus 1 would be 2.780. And 2 to a power of 2, not quite 3. Well, 2 to the third is 8. Yeah, so that's very sensible. That makes, I'll put a little check mark there. I'm happy with that answer. So, you can see how logarithms are important. They're used to solve exponential equations, and it's a pretty similar process every time. You just take the log of both sides, use that power rule, which comes in very handy, isolate the x, go through your regular equation solving techniques, and you'll have the answer. All right, we'll take a look at some tougher problems next time.